Okay. So, left it off with some examples last time. Let's actually run through those. Integral of 1 over x squared, integral minus 3, integral of 1 over radical x squared plus 4x plus 8, integral of dx over 4x squared plus 1. Start with those for now. Okay, what do we do here? A1. A. What do you try? Yeah?
Set A equal to 3, so you replace x with 3 secant 3.
Well, yes, so we can think of the 3 as the square root of 3 squared. And so this thing here, it looks like an x squared minus a squared form. And so the proper substitution would be
Root 3 secant 8.
So that reminds us of secant squared minus 1, which is going to give us that tangent. And yeah, so we would have our dx would be derivative of secant.
Secant to the 10th.
D theta. And so we're going to go back to this integral, we're going to plug all that in. So we have that 1. We have x squared, but x is this guy, so this is 3 secant squared. We also have the square root of, well, plug this in for x squared, that's going to be 3 secant squared theta minus 3. And for our dx, we are going to have radical 3 secant theta tangent theta theta. So we have that guy. Now, of course, the secant squared minus 1 is going to become tangent, so that guy just simplifies to radical 3 tangent theta. Now we start simplifying. So, tangent, tangent, radical 3. This constant 3 here can be factored out. And so also secant, you can cancel one of these secants. And so we pretty much have, when it's all said and done, dust settles and we're left with what over here? Cosine. So this guy reduces to cosine under the right trig sub. Radical 3 secant theta, and hopefully remember how to integrate cosine. What do you get? Sine of theta plus c. However, we need to get back to x. How do we do that? How do you go back to x? How does the back substitution work?
You go back to the original substitution and you find out.
Okay, so that x is equal to the radical 3 secant.
And then you can set secant equal to x over 3. And then if you want, you can change it to cosine.
Sure.
You don't have to. And then you can make a triangle.
Yes. Love how you're giving me options. You can do this if you want. You don't have to. Give me options. That's good. So that gives us a triangle here where we can think of the adjacent is radical 3.
That's the opposite.
That's the opposite. And the hypotenuse is x, which means that by Pythagoras' theorem, this is going to be x squared minus radical 3 squared. And so from this, if we can get the sine is going to be opposite over adjacent, or opposite over hypotenuse, which is going to give us radical all over x. And so then we just go back and we plug that in. So it's the square root of x squared minus 3 all over 3x. That's our antiderivative. So basically there are those three situations that we're always looking for. So this is just a reminder of what happened last time. X squared minus a squared minus x squared, and x squared plus a squared. This guy's a secant theta substitution. This guy's like an a sine theta substitution or a cosine theta substitution, even though they don't really use that much. And this one is just an a tangent theta substitution. And we saw that expression here. Now, of course, not having a square there in general is not a problem. We can put one in by just throwing in a radical. Second one. What do we do here? Yeah?
When you complete the square on the bottom,
You can complete the square. What would it become?
x plus 2 squared plus 4.
X plus 2 all squared, which we know is x squared plus 4x plus 4. And to get back the 8, we add a 4. And now what? Yeah,
You can set x plus 2 equal to 2 tan theta.
right. Because the 4 we can think of as 2 squared. So this looks like an x, right? Now, this example, and I think I had a couple others, was meant to show you that you don't have to literally have x. Just something that's a variable and changing squared plus a constant squared. That kind of reminds us of this guy, which tells us that we can make this into a tangent substitution with x plus 2 as the variable. So I can set x plus 2 equals to 2 tangent theta. And so differentiate both sides, dx equals 2 secant squared theta, d theta, and then we start to plug these guys in. So in the denominator we have 4 tangent squared plus 4, and for the dx we have 2 secant squared theta d theta. And this now becomes, so factor out of 4, you get tangent squared plus 1, which we know is secant squared. Your radical everything, you're going to get 2 secant times 2 secant squared. 2 cancels, secant cancels 1 and secants. We end up with secant theta. What's the integral of secant theta?
ln of secant plus tangent.
ln of the absolute value of secant theta plus tangent theta. Now that is in theta, we need to get these back into x's. So we're going to do, again, our whole back substitution fiasco. So we have that x plus 2 all over 2 is going to give us our tangent theta. This means that we can construct a triangle where x plus 2 is the opposite and 2 is the adjacent, which means the hypotenuse is going to be the square root of the sum of the squares. So that actually gives the x squared plus 4x plus 8 back over there. And from this I can figure out the secant and the tangent. This implies that the secant of theta, which is going to be the hypotenuse over the adjacent, and the tangent, which we already have here, is x plus 2 over 2. And so we go back, we plug those guys in, and we would have ln of x squared plus 4x plus 8 all over 2 plus x plus 2 all over 2 plus c. And now, probably, if you're looking at this as an answer in the back of your textbook, they'd probably bring it to this point, x squared plus 4x plus 8 plus x plus 2 plus c. They will leave that as the answer. Why is that valid? Why could I do that? Why are those two the same from an integration perspective? Guys are so boring. Does anyone see what I did to go from the one right above to the box? What are you thinking here? No idea? Or do we know and we just very shy? No idea. Does this help? Can combine fractions inside the LN? Does that trigger anything?
Why can't you multiply by 2?
No, do you see that this is the same as that?
You just have
Yeah,
to-
so now, given that, what do you think? Yeah?
Could you like split it like the natural log of the top thing minus the natural log of the bottom thing?
Right, that's a log rule.
As equals plus c.
Right, there's a rule that says log of something divided by something is equal to the log of the first thing minus the log of the second thing. Right? So that splits into that. And why is that equivalent? Well, ln of 2 is just a constant. So I just call this whole thing a new constant. Okay. So there are times when your book might write the answer in a slightly different way, and you're like, I don't understand what's going on. They're applying some sort of rule to simplify things. Log and exponential rules, very important, you have to remember them. Always have them in front of your mind. Okay, this one, what do we do? Yeah.
So x is 2x squared plus 1 squared.
So the 4x squared you think of as 2x squared plus 1 squared?
Yes.
Yeah. And so?
And then you do 2x is equal to 1 tangent theta, and then
So-
derivative of both sides.
Right. So we have 2 dx equals to secant squared theta d theta. or I can move this to the other side and say this is equal to 1/2 of that. And then I go and I start plugging these guys in. So 1/2 secant squared theta d theta replaces my dx divided by the radical of the 2x is just tangent theta, so this is just tan squared theta plus 1. We know tan squared plus 1 gives us secant squared, and then we take the radical, so that gives us just secant. That cancels. Again, we end up in the situation where we're integrating secant theta d theta, and so we're going to get this back, but the triangle is going to be set up differently. And besides, this is 1/2. And so now we're going to go to figure out what these thetas are. We know that tangent theta is equal to 2x. You think of this as 2x over 1. And so set up a right triangle here. This is the opposite, this is the adjacent. The hypotenuse would be the square root of the sum of the squares, which gives us the 4x squared plus 1. And so I can find the secant from this, which is going to be adjacent, hypotenuse over adjacent, which is just going to be 4x squared plus 1 over 1. And so I can go back and I can plug this in. So this is 1/2 ln of the secant square root of 4x squared plus 1 plus the tangent, which is 2x. That's that one. So you can find the derivative of that. It's a trig sub. And the next one. Okay, so d integral of dx over x squared plus 1 over 2. Now, of course, we're integrating 1 over x squared plus 1. That's easy. That's just a general formula, arctangent of x plus c. But now I raise that thing to the 3 over 2 power. What do we do now? You tried it, tell me what you tried. Yeah?
X equals tan theta.
Makes sense? Your dx would be secant squared theta, d theta. And you just go and plug that in. And that will be tangent squared theta plus 1 to the 3 over 2. And we know that that would give us secant squared theta to the 3 over 2. And that would cancel with that. And so we would get secant squared theta d theta over secant cubed theta. So we get 1 over secant. Again, that's not so bad. This is cosine. Integral of cosine is sine. To figure out what the sine is, we are simply going to take the fact that, do the back substitution, tan theta equals x, think of that as x over 1. I can set up this triangle. opposite over adjacent, and this is going to be the square root of the sum of the squares. And so I can take the sine of theta, that's going to be opposite over hypotenuse. And I go back and I plug it in. That's the answer over there. More to do, get through. So you really want to just do a bunch of these so it starts to become, just keep doing them until they become easy, is the idea. Okay, the first one. What do you do?
A equals root 3, x equals root 3 secant theta.
X equals radical 3 secant theta. So our dx is going to be radical 3 secant theta tangent theta d theta. Now what?
Plug it in.
Well, this is a definite integral. Probably what I would do is I would change the limits. Now, technically speaking, changing the limits is an optional thing. You can always just find the answer in terms of x and then plug in the old limits, except probably I would say for trig substitution, always change the limits. That's all capitals. You don't have to, it's recommended. Highly. Okay. Because once you change the limits, what that does is it saves you from having to do the back substitution part. Because to remember, when we get our answer in theta, to get the answer back into x, we have to draw a whole triangle, and we might have to be doing some before and all kinds of things. You can avoid all of that by just changing the limits right up front. And so once you get an answer in theta, you just plug in the numbers that correspond to theta right away, and it'll save you a lot of time. So that's one thing. If you're going to attack an integral by trig sub, and it's a definite integral, I'll definitely always change the limits. Some people like to not change the limits and then just wait till the end and plug in the old numbers, but this is highly recommended for trig sub. It'll save you time. So how do we change the limits? How do we change the limits? Yeah?
You could solve the x function for theta and then put in the x's to find the theta
Yeah.
values.
So you're like, when x equals 2, you're going to have 2 equals radical 3 secant theta, and so you're going to have 2 over radical 3 equals secant theta, and you're going to have, basically, you can flip this, cosine theta equals radical 3 over 2. That means theta equals what? Yes, but that's a value that we know.
Cosine of root 3 over 2.
Yes, but that's a, there's a we know, huh?
25.
It's not 35 degrees, yeah.
5 or 6.
Yes. You guys need to remember the trig values. We're gonna cover a topic with, called polar coordinates, where we're gonna be doing a lot of trig. So the trig rules, things you have to start looking up, the special angles and all that stuff. You know how to get the angles and all that good stuff. Radical 3/2 is a nice value. We actually know exactly what that is, so it's pi over 6. When x equals radical 3, then what we have is radical 3 equals radical 3 secant theta. Then we have basically that secant theta equals 1, which basically also means that cosine of theta equals 1, which also means that your theta is 0. Now here it's okay to pick any number that gives it. So, I mean, technically you could also pick 2 pi, but 0 is a nicer number to use than 2 pi. So I would actually change the limits. So now when I'm plugging it in, I'm plugging it in with these new limits, so I don't need to go back to x's at the end of the day. So instead of radical 3, I am going to have 0. And instead of 2 at the top, I'm going to have pi over 6. Now I'm going to plug these guys in. So my x was radical 3 secant, so this is just 3 secant squared minus 3 over x, which is radical 3 secant, times the dx, which is radical 3 secant theta tangent theta, d theta. This all cancels with that. So you can factor out the 3 here, you're going to get secant squared minus 1, that gives you tangent squared, and then we take the square root of everything, so we get radical 3 tangent times tangent. So now we have 0 to pi over 6, radical 3 tangent squared theta d theta. How do we integrate tangent squared? Yeah?
Use identity. So you got square root minus 1.
So this is secant squared minus 1 d theta, and the integral of secant squared? Huh?
Tangent.
It's tangent. The root of tangent is secant squared, and the integral of the 1 is theta, because it's d theta. And now, we don't have to go back to the triangle thing, because we actually change the limits to correspond to theta. So I can literally now just directly plug in the pi over 6. It's going to be radical 3 times tangent of pi over 6 minus pi over 6 minus parentheses tangent of 0 minus 0. There's another bracket here. Okay. Tangent of 0. What's tangent of 0? 0. So this is just 0 minus 0, so that's 0. What's tangent of pi over 6?
1.
No.
1 by
No.
3.
Are you just guys just randomly guessing, or do you like have a legitimate guess?
1 over 2? Or 2?
1 over 3.
It's 1.
So one, you can remember that tangent is actually sine over cosine. So what is sine of pi over 6? Yeah, it sounds so unsure. So sine of pi over 6 is 1/2. What's the cosine of pi over 6? Radical 3 over 2. We actually did it over there. Keep, change, flip. That becomes 1 over radical 3.
That's what I said.
You guys need to remember all that stuff, really. Like, you're gonna die when we hit polar coordinates if you don't remember all that stuff. You really need to go back over your trig. Know all the special angles, know all the graphs, know all that good stuff. So that becomes that. You can multiply out that and write 1 minus radical 3 pi over 6 if you want, but that's fine. What about, so yeah, highly recommend, if you have a definite integral and your approach is a trig sub, you definitely want to change the limits. It'll save you some time. Let's, okay, what did we do here?
Completed the square for this one too.
How do you complete the square in this case?
I pulled out a negative and then I just, so I have -1 times x plus 2 squared plus 4.
And so you can complete the square inside these parentheses over here, which would look like x plus 2 all squared. That would give you the x squared plus 4x plus 4, but since there's no plus 4, there's a minus of 4. And so this leaves us with 1 over the radical of 4 minus x plus 2 squared dx. Yes, completing the square. You need to know your algebra in general. You need to know your trig in general. Everything you've ever learned, you need to remember, basically. From algebra, pre-calc, and calc 1. Log and exponential rules, all that good stuff. Okay, so now that we've brought it to this situation, what are we going to do?
X plus 2 equals 2 sine theta.
All right, this looks like the a squared minus x squared. So we would set x plus 2 equals 2 sine theta. So your dx would be 2 cosine theta d theta. And so we would end up with, in the denominator, this is 4 minus 4 sine squared. In the numerator, the dx will be replaced by 2 cosine theta d theta. So you can factor out the 4, you get 1 minus sine squared, that changes to cosine squared, you have 4 cosine squared under here, then you take the radical. It just becomes 2 cosine theta. And that cancels. It's just 1 d theta. Integral of that is theta. And what's theta here? We know that 2 sine theta is equal to x plus 2. This means that sine theta is equal to x plus 2 over 2. This means that theta is equal to the sine inverse of x plus 2 over 2. And so this guy simplifies to arc sine. Let's see. That's that. I think that was the last example, right?
Yeah.
Okay, that was the last example. Make it through. At least I don't know. I or silent. I'm not sure if you're quiet because most of you actually try the problems, or you're just shy. I don't know. I guess only time will tell. The next quiz will probably tell. If you're not practicing the problems and I ask you to practice them, that's a great way to have your grades go like this. Just paying attention and copying the solutions in class isn't enough. You have to actually try it on your own. Let's move on. That was the last example. I do want to say something else about trig sub before moving on to the next section. So I will mention that now. And that topic is to trig sub or not to trig sub. That is the question. Now, once you learn about trig sub, you're going to start seeing that expression, the x squared minus a squared all over the place, or a squared minus x squared, or x squared plus a squared. And you might have the reaction of going the trig sub way, and there are even sometimes where like a textbook will go through a solutions for something and they will do it the trig sub way when they actually don't have to. So here's how you know when you need to do trig sub, because if you're doing trig sub and you don't have to, chances are you're taking longer to solve a problem than you need to. And so here to several guys here. So, now in all of these integrals, they actually contain the pattern of x squared plus a squared, namely in the form of x squared plus 4, which is x squared plus 2 squared, x squared plus 2 squared, x squared plus 2 squared. They all have the form that a trig sub could work. You can solve all of these integrals by trig sub, but the thing is, you wouldn't, at least not if you want to be efficient. You think you can get away without using a trig sub here? Or which one would you say is more likely a candidate for trig sub versus not? Where would you use trig sub? Which one? Yeah?
The first one.
Use it on the first one? What about the second?
I didn't think it fully through, but I think u sub might be able to work.
Right, like a u equals x squared plus 4?
Yeah.
The du is going to be 2x.
And
You
then
can always factor off the 2, you're going to be left with that x, right?
and then
That'll save you from the back substitution, drawing triangles, getting a trig function, doing a trig integral. You just do a regular u sub and then it's power rule, right?
and then that one.
So trig sub is definitely not what you would do here. This is definitely a candidate for u substitution. Or u substitution is a bad way to call it, just regular substitution. So if I see that, I'm not doing a trig sub. It's going to take a lot longer. What about this one?
Same. You could use x cubed as u, and then actually no, it wouldn't work.
X squared will be u minus 4.
X squared would be what? You use a trig sub for
Or
this?
could you do, if you make u x squared plus 4, and then the derivative is 2x, but you separate the top into x and x squared,
U equals?
x squared plus 4,
Mm-hmm.
and then du is 2x dx, and then
So one x.
the top separates into x times x squared. And
Yeah.
then x squared could be, or
U minus 4.
u minus 4.
And the x would cancel out.
And the x
And
is-
so this all would result in 1/2 times the integral. If we're going by all the suggestions so far, u minus 4 over radical u du, right?
which you could just multiply.
And that's just a half power dividing each,
Yeah.
and again, power rule. So it could also work. Probably a little bit nicer way to have done that with a regular substitution is to do something like u squared equals x squared plus 4. Then you'd have 2u du equals 2x dx. You'd have u du equals x dx. Now again, from this, I'm going to see that my x squared is u squared minus 4. So now when I go and I start to plug those guys in, the x squared gets replaced with u squared minus 4. My x dx gets replaced with u du. And the radical of x squared plus 4 would be replaced by u. So this cancels. And that's even nicer. No radical powers, no fractions to worry about. But yeah, another thing here is this is a regular substitution. Regular. Not that it can't be done by trig substitution. These can be done by trig substitution. It'll just be a much more inefficient way to do it. Right? And if I gave you these problems on a quiz, in my mind, I would think, oh, they'd recognize they were regular substitution, not trig substitution, and so when I'm thinking about the time that it would take the average student to finish the quiz, in my mind, I'm timing for a regular substitution. Whereas if you do trig substitution, you're going to go over time. You're going to end up being rushing, and it's just, you're going to be more stressed than you have to be. Do you see the kind of deciding factor? Yeah.
Matching powers?
Matching powers? What do
I
you
mean,
mean?
technically it's in a radical, but between these three, the only one that we chose for trig sub was the one where you have an x squared both in the denominator.
So as long as the powers match, we have to use trig sub? What about the following? Let's go like one step up. What would you do with that? Can a regular substitution work?
Could also have to do with the even or odd functionality.
Yeah, well think about this situation. Which one would you do? If this was the problem. Would you opt for a substitution or a trig substitution?
Well, if you did regular substitution, then you would end up with an extra x, because we would.
Right, so if you were to jump into a regular substitution, what would happen? You'd end up with, like what? You want to do a u squared equals x squared plus 4? Now this would mean that if you differentiate both sides, 2u du equals 2x dx. So your u du equals x dx, much like before. Now we can get rid of an x. So this here is going to be an x cubed times x, where this x dx is just going to be replaced by u du. But now what do we have? What do we do with the x cubed?
Well, two of them.
Okay, so you're going to think of this as x times x squared.
Yeah, but then you sub.
One gets
x.
out with a substitution. One gets replaced by just u squared minus 4. What about this guy? What happens?
Square root of u squared plus 4. Minus 4.
And what would you do in that situation? Essentially, you just return to a situation where it's like probably a trig sub will work at this point.
Yeah.
Right? Because that was gonna make me, because I'm like, a regular substitution isn't cutting it because there's always gonna be this extra guy left over. And so eventually I'm gonna get it to a point where I'm just like, man, I give up trying to avoid trig sub. Let's just do the trig sub. And at this point you would have done u equals 2 secant theta. But the thing is, if you resulted in doing that anyway, might as well you had done it from the very beginning, right? And so this is also another situation in which I would use trig sub, right? Not necessarily because I'm a fan, but it's more efficient, right? So now do you see the deciding factor?
Is it,
Yeah.
those powers are either even or odd?
Yeah, so use, maybe I should say, state it in terms of the negative. If your integrand contains an odd power of x, regular substitution works. Opt for that. If only even powers appear, then what's going to happen is you'll always have this extra variable left over after a trig sub, after a regular u sub, in trig sub. Okay. Now, in general, it's really nice if the odd power is in the numerator of the integrand. You can get away with doing a regular substitution, even if I had the x cubed in the denominator. It's just that to fully solve problems like that, you will tend to actually need another extra piece of technique, which probably wouldn't be worth it in the end, but you'll actually need the next topic, which is going to be partial fractions. So there are times when you can get away with an odd power being in the denominator, but it's probably still simple. Simpler to do trig sub in that case. So pretty much if I have an odd power of an x, so if I have like an x to the fifth, an x to the seventh, an x cubed, or an x, I would do a regular substitution, not a trig substitution. Because by doing the regular substitution, that's going to change that to an odd power. I have the even powers left over, which I can solve for in an equation, and I end up in a much nicer situation. Right? So just because you have all these techniques doesn't mean you have to always use them. With great power comes great responsibility. All that good stuff. So trig sub can get you out of a bind, but like I said, because of the back substitution component and you having to do an extra step by using SOHCAHTOA to figure out certain expressions, you probably avoid it when you can. But if you can't avoid it, make sure you know how to do it properly. Let's actually segue into the other one, which allows us to even deal with situations where the x is in the bottom. We are going to do 7.3. So partial fractions. So let's look at some motivation here. Why would I want to learn a whole other integration technique? Consider the following. That's a nice motivating example. Okay. Now, based on what we have so far, how would you attack that integral? Well, that's you. At this point, done so far, point, probably your best bet for actually attacking an integral like that would actually be trig substitution, right? Because sure, you can take a u equals the denominator, but then you'll get a 2x and a minus 5, and you don't have those guys. Integration by parts, I don't see how that's going to work. And yeah, pretty much trig substitution. So we got in the situation, I gave you a couple examples last time, where we just had a radical of these random quadratics, and the goal and what we did was to attack that is to complete the square. So one option is that you can actually complete the square, but that's a 5. It's going to be slightly annoying, but it's not going to stop us. That is just minus 5 over 2 squared, right? Half the coefficient of x. Then realize that when you square that, you are going to get a 25 over 4. And so you have to realize what's left over here. 6 is going to be what over 4? Well, this is 24 over 4, right? So it means that to get the 6, I can think of this as 25 over 4 minus 24 over 4. And so what happens is I'm left over with an extra 1 over 4 here, which I can rewrite as 1/2 squared. So now I'm in a situation where by completing the square, trig substitution can actually deal with this guy. Just let x minus 5 over 2 equals 1/2 secant theta. Now, obviously that's pretty annoying. However, check this out. Let's look at this integral another way. Turns out that this is equal to that. Right? Now, if you don't believe me, you can actually do the rules. X minus 2 minus x plus 3, that gives you 1 in the top. Multiplying the denominators will give you x minus 3 times x minus 2, and that will give you x squared minus 5x plus 6. These two fractions adds up to that fraction. And so, it turns out that if I see this, hey, I could actually just think of it like that. Then, how would I integrate these individual components? What's the integral of this?
ln x minus 3.
ln of absolute value of x minus 3 minus ln of absolute value of x minus 2 plus c. And we're done. Yeah, everybody got it? That's partial fractions. Moving on to the next section. Kidding. I'm going to show you how you would do this, okay? So there's a method to go from a situation like this to a situation like that, and that is called the partial fractions decomposition. Okay? So again, there is often more than one way to skin a cat, but some ways are nicer than others. And if I have to choose between doing a trig sub with a bunch of fractions in it, or doing this, where it's just easy to see the answer right away, I'm going to choose this all the time. Right? Let us see how this can be done. So given a rational function say p of x over q of x, if we break this up into a sum of smaller fully reduced fractions, we say we've found partial fraction decomposition. So that's the name. Okay. So if we have x squared minus 5x plus 6, and you would notice that this is the same as x minus 3 minus 1 over x minus 2. The process of moving from this scenario to that scenario is called the partial fraction decomposition. process of moving from this scenario to that scenario, well, that's a very complicated thing. It's called addition. Or combining the fractions, right? So partial fractions is going to be a method by which we can deconstruct a fraction into smaller fractions. And the idea being, these smaller fractions will be easier to deal with in any computation that we want to have to deal with them in. And in particular, when it comes to integration, having smaller fractions is usually a better thing. And we're going to be looking at much nastier fractions than this one. But now I'm going to explain to you the process of actually going from one step to the next step. How do you go from here to there, the thing that I erased? So now I'm going to teach you the method of partial fractions. It's going to have to tell you in separate stages here. So, step one could be step 0, but whatever. The first thing you want to do is to make sure you have a proper fraction. i.e., the degree of p must be smaller than the degree of q. If not, reduce first. This may require long division of polynomials, so we're going back to that again. Or synthetic division, if that's what you learned and that's what you remember, that's fine, but I like the long division way. Or some algebra. So, examples of that situation, let's say you have something like x squared divided by x squared plus 4. Now that fraction is not proper because the degree of the top is 2, the degree of the bottom is 2. It is not the case that the degree of the top is less than the degree of the bottom. So rather than worrying about breaking that up into little nice fractions, you'd probably want to simplify first. Now there was a problem similar to this on the homework. How did you guys actually deal with it? Or the integral of that thing? Yeah.
You can put plus 4 minus 4 in the numerator.
Yeah, just do your algebraic trickery, add and subtract 4.
And
Now what that allows you to do, right, is you can now split the fraction into 2 pieces. And so that would become, let's just write out that, x squared plus 4 over x squared plus 4 minus 4 over x squared plus 4. This of course reduces to 1, so it's 1 minus 4 over x squared plus 4. And so now this is a reduced fraction, and that is just a constant. And by the way, if there was an integral sign in front of the whole thing, I would just write it as this. And here I don't really need anything really fancy. That's going to be an arctangent, and that's going to be x. So if the power on the top is greater than or equal to the power on the bottom, you can actually reduce it, and you might not have the need to do a process like what I'm going to describe. Now, something like this, cleverly adding and subtracting something, it works very nicely when the powers on the top and the bottom are the same, right? So you can kind of recreate the top by just adding whatever you need to make the top look like the bottom, and then subtracting all the things you added so that you didn't actually change the value. So even if this was like something like x squared over x squared plus 2x plus 3, what I'd probably do is I would add 2x plus 3 and then subtract 2x and 3, right? And that would break down into 1 plus 2x minus 3 over this, right? And that breaks it down again. So that's a nice trick. Now if the power in the top is larger, probably you would need something more. Sometimes this trick will work on certain things if you can see it. But sometimes you might need a little bit more sophisticated machinery like long division. So for example, if I had instead x cubed over x squared plus 4, it's not exactly clear what I need to add and subtract to the top of that to actually make that look a little bit nicer. So what I would do in this situation is something like polynomial long division. Now, I'm going to go through this process, but it is not meant to teach you this process. It's something that's actually something I kind of expect you to remember. If you don't remember this weekend, that's another thing to add on your list to study, as well as angles to trig functions and all that good stuff. So, this is x squared plus 4. You put x cubed under here. You want to divide the x squared plus 4 into the x cubed. Does anyone remember how to actually do this? Take the first guy, divide into the first guy. X squared divided into x cubed goes x times. You're going to take that x, you're going to multiply everyone here. So you're going to get x cubed plus 4x. Now, technically what you want to do is you want to line these things up, because otherwise you can get in trouble. So a nice thing to do is to write some placeholders. Technically there's a 0x squared and a 0x and a 0. So divide the first guy into this, you get the result, take that result, multiply everyone here, you would get x cubed plus 4x. I'm going to line up the 4x with these x over here. And then what you're going to do is you're going to subtract that line from the line above. X cubed minus x cubed, those die. 0x minus 4x, you get minus 4x. Okay? Now, notice here that if I try to do that process again, x squared divided into this, it does not divide into that, because the x squared is larger than that. And so I would stop the process. This would be the remainder. And so now what we would be able to say is that the x cubed over x squared plus 4 is equal to x plus minus 4x over x squared plus 4. And clearly you can see that that would be a lot easier to integrate than that. And for those of you who remember long division, the comparison, it's a direct comparison to long division. So if I had to say, what is 27 over 2? What I would do is I can put the 2 here, 27 there. I put the first guy into the first guy, 2 into 2 goes 1. 1 times this is 2. I subtract that. I would get 0. Move the 7 down. 2 into 7 goes 3. 3 times 2 is 6. Subtract that. Remainder would be 1. 2 into 1 you can't. So that's actually the remainder. You stop the process. And so the answer is going to be 13 plus 1 over 2. Right? Same idea. What we're doing with polynomials. So if you have something like this, you need to break it down. The partial fraction method is not going to work if the power on the top is greater than or equal to the power on the bottom. So that's step 1. Like, make sure you have the right form to even start the process in the first place. Step 2. Factor the denominator completely. If you have problems with factoring this weekend, make sure you look over that. That's it, that's step 2. Step 3. You're now going to break up the big fraction over each factor in the denominator. There is an important requirement here. The numerators will be arbitrary expressions 1 degree less than the factor in the denominator. Let's do some examples of that. So, the original example we had was x squared minus 5x plus 6, right? The highest power on the top is actually smaller than the highest power on the bottom, so I can go into this process. The first thing I'm going to do is I'm going to factor the denominator. So you know that this is factoring x and x. I think the two numbers that add, that multiply to give you positive 6, they add to give you negative 5. Turns out minus 3 and minus 2 are those guys. Now what you're going to do is you're now going to split the denominator into these factors that you've just created. Now what you put in the numerator is going to be arbitrary. You don't really know what the numerator is going to be in before you actually calculate it. So I'm just going to put like an A here. I'm going to put like a B here. And that's the expression. So I know this guy is going to split into two things that look like that. Now the goal is going to be to find A and B. The previous example shows you that A was positive 1 and B was negative. But we're not there yet. The first thing is to basically break it down. Let's look at another example to fully explain the double star. So you fully appreciate what I meant by A and B. If I had, so this is an example. Here's another example. If I had, say, 1 over x cubed plus x, I would realize 1, the highest power on the top, is smaller than the highest power on the bottom. So next step is to factor the denominator completely. This does not factor over real numbers, and we don't care about complex numbers, so that's fully factored as far as we're concerned. So the next step will be to break this into two pieces. One piece will have denominator x, the other piece will have the denominator x squared plus 1. Now over the x we would just put a. I don't know what that number is. Now, because the numerator must be 1 degree less, specifically 1 degree less, what should the numerator of this guy look like?
ABS.
bx plus c. We're going to put the most general form of what's 1 degree less. If the denominator is quadratic, the top must be linear. If the denominator is cubic, the top must be quadratic. If the denominator is a fourth power, the top must be, you get the idea. So that's how that would split up. If it's something like 1 over x times x cubed, something that doesn't really factor nice, plus 2, that doesn't factor very nicely. You would break that up into a over x plus, here this is x cubed plus 2, you're going to do bx squared plus cx plus d, right? Your numerator must be 1 degree less specifically than the denominator. It can't be a cubed or anything bigger because that brings you back to step 1. However, if you pretend that it's anything lower than 1 degree less, you can potentially miss some information because it's possible that there was a square on top. You don't know. So you want the most general situation that it could possibly be to be a proper fraction. That means you have to go 1 degree less. So that's step 3. So make sure it's proper. If not, do a long division or do algebra magic. Step 2, factor the denominator. Step 3, you're going to break it up into the factors of the denominators, making sure that the top is 1 degree less. 3b, we will pretty much going to end here, so we'll finish the last leg next time. One thing you want to realize, if factors are repeated, you must, this is the shortest way I can describe it in words, count up with the fractions. I'm going to show you what I mean by that. So here's what I mean by that. Let's say you have 1 over x times x plus 1 squared. The x plus 1 squared, this you think of as a repeated factor. Right? It's repeated once. Right? So it's factored, but there are 2 of them there really. Right? So whenever you have a repeated factor, you have to count up to the power. So I would split this into x x plus 1 and x plus 1 squared. So I start at the first power and count up till I get to the second power, because there are two. Here I would put A, B, and C. Because the numerator obeys the rule for the factor. So this factor here is linear, which means the numerator needs to be a constant. If it were something like x times x plus 1 cubed, again you're going to do this count up idea. Start with x plus 1, go to x plus 1 squared, go to x plus 1 cubed. And that's going to be A, B, C, D. Yes?
Why is it only C and not C plus D since it's
Let me explain it in this way. What if I only had 1 over x plus 1 squared? Apply this rule here. The nice way to do it would be to actually use x plus 1 as the variable. So you do ax plus b, and that's going to split up into a so that a process like that happens for the cube, for the square, for everything. You can actually just replace the variable with each factor, and it automatically breaks down. So you end up with this situation. If you had something like then this would be a over x plus bx plus c over x squared plus 1 plus bx plus e over x squared plus 1 squared. Now the rest of that is just actually algebra to solve for the a, b, c, d, and e, but that we'll cover next time. That's going to be the last leg. So read these steps very carefully. It's very important that you apply them how they're meant. We'll pick up next time.
How did you say my name for it?
Did I?